Tonight, we begin a gentle journey through one of the most profound questions humanity has ever asked. As you settle into comfort and let your mind drift among the stars, we'll explore together a mystery that has captivated astronomers for decades. How many worlds like our own Earth might exist right now, spinning quietly through the cosmic dark, perhaps harboring the delicate chemistry of life itself? This isn't a question born from science fiction or wishful thinking. It's a genuine scientific inquiry, one that has transformed from pure speculation into careful observation and measurement. In the soft glow of our most advanced telescopes, we're beginning to glimpse an answer that would have seemed impossible just 30 years ago. Take a moment to breathe deeply and imagine yourself floating peacefully above our planet, looking down at the blue marble that cradles all known life. From this gentle perspective, Earth appears unique, precious, and impossibly rare. Yet, as we'll discover together tonight, the universe may be far more generous with worlds like ours than we ever dared to hope. The story begins quietly in the early 1990s, when astronomers made their first tentative discoveries of planets orbiting distant stars. These weren't the gentle, Earth-like worlds we might hope to find, but strange, massive planets unlike anything in our solar system. Yet these early discoveries opened a door that has never closed, revealing a universe far richer and more complex than we imagined. Today, as you rest comfortably, scientists have confirmed the existence of over 6,000 planets orbiting other stars. Each one represents a world with its own story, its own unique combination of size, temperature, and orbital dance around its parent star. Among these thousands of confirmed worlds, we're beginning to identify those that might, just might, share some of Earth's most precious characteristics. But what exactly do we mean when we speak of an Earth-like planet? The definition is more nuanced and beautiful than you might expect. It's not simply about size or distance from a star, though these factors matter enormously. An Earth-like world must exist in that delicate zone astronomers call the Goldilocks region, where temperatures are neither too hot nor too cold for liquid water to exist on the surface. Picture, if you will, a cosmic balancing act of extraordinary precision. Too close to its star, and a planet becomes a scorching desert where any water boils away into space. Too far away, and it transforms into a frozen wasteland where water exists only as ice. But in that narrow band of space around each star, there exists a zone where water can remain liquid, where rivers might flow and oceans might sparkle under alien skies. Our own Earth sits comfortably in this habitable zone around our Sun, at a distance that allows for the liquid water essential to all life as we know it. But Earth's habitability depends on so much more than distance alone. Our planet's atmosphere creates a greenhouse effect that warms the surface, while our magnetic field protects us from harmful radiation. The size of our planet gives us just enough gravity to hold onto our atmosphere, while our moon stabilizes our rotation and creates the tides that may have helped early life develop. These discoveries about exoplanets, as we call worlds orbiting other stars, come to us through several elegant methods that showcase humanity's ingenuity and patience. The most successful technique is called the transit method, a process as gentle and rhythmic as watching shadows pass across a window. Imagine sitting by that window on a peaceful afternoon, watching the subtle changes in light as clouds drift by. In a similar way, astronomers watch thousands of stars simultaneously, looking for the tiny dimming that occurs when a planet passes between the star and our telescopes. This dimming is incredibly subtle, often less than 1% of the star's brightness, lasting only a few hours as the planet completes its transit. The precision required for these observations is breathtaking. We're measuring changes in starlight so small they would be like detecting the shadow of a firefly passing in front of a lighthouse from hundreds of miles away. Yet our instruments have become so sensitive, so carefully calibrated, that we can not only detect these tiny signals, but also determine the size of the planet, its orbital period, and even begin to analyze the composition of its atmosphere. Another method, called the radial velocity technique, listens for the gentle gravitational whispers between stars and planets. As a planet orbits its star, it causes the star to wobble ever so slightly, like a dancer spinning with an invisible partner. This wobble shifts the color of the star's light in ways we can measure with extraordinary precision. Through these subtle color changes, we can determine not only that a planet exists, but also estimate its mass and orbital characteristics. Each confirmed planet represents months or years of careful observation, mathematical analysis, and peer review. The process is methodical, patient, and beautifully collaborative, with astronomers around the world sharing data and confirming each other's discoveries. This scientific approach ensures that when we speak of the thousands of confirmed exoplanets, we're discussing real worlds, not wishful thinking or measurement errors. As we've refined these techniques and launched more sophisticated space telescopes, the pace of discovery has accelerated dramatically. The Kepler Space Telescope, launched in 2009, revolutionized our understanding by monitoring over 150,000 stars simultaneously. Its successor, the Transiting Exoplanet Survey satellite, continues this work with even greater precision, scanning the entire sky for planetary signals. These missions have revealed that planets are extraordinarily common throughout our galaxy. Nearly every star we observe appears to host at least one planet, and many stars host entire families of worlds. This abundance suggests that planet formation is not a rare cosmic accident, but a natural consequence of how stars and solar systems develop. The diversity of these discovered worlds is remarkable and humbling. We've found planets larger than Jupiter orbiting closer to their stars than Mercury orbits our Sun, completing their years in just a few Earth days. We've discovered planets orbiting binary star systems, where beings on the surface would witness two suns rising and setting. We've even found planets orbiting the dense remnants of dead stars, worlds that somehow survived their star's explosive demise. Among this cosmic menagerie, we've begun to identify planets that might be more familiar, more Earth-like in their characteristics. These worlds are typically rocky rather than gaseous, similar in size to our own planet, and orbiting within their star's habitable zone, where liquid water could exist. The search for these potentially habitable worlds focuses primarily on two types of stars. The first are stars similar to our own Sun, known as G-type stars. These stellar neighbours burn steadily for billions of years, providing the stable energy output that might allow life to develop and evolve over cosmic timescales. The second category includes red dwarf stars, smaller and cooler than our Sun, but far more numerous throughout the galaxy. These diminutive stars burn their fuel so slowly that they can shine for trillions of years, providing potential habitats that would last far longer than our Sun's eventual lifetime. However, planets around red dwarfs face unique challenges, including intense stellar flares and the likelihood of being tidally locked, with one side permanently facing their star while the other remains in eternal darkness. Current estimates suggest that our Milky Way galaxy contains somewhere between 100 and 300 billion planets. This staggering number represents our best scientific estimates based on the planetary systems we've observed and statistical models that extrapolate from these observations to the entire galaxy. To put this in perspective, if every person currently alive on Earth were responsible for studying just one of these planets, each of us would have more than 10 worlds to investigate. The sheer scale of planetary abundance in our galaxy alone suggests that Earth-like conditions might be far more common than we once believed. But abundance doesn't necessarily mean habitability. Among the thousands of confirmed exoplanets, only a small fraction appear to be both rocky and located in their star's habitable zone. Current data suggests that roughly 200 of the confirmed exoplanets are classified as terrestrial or rocky worlds. This number reflects both the genuine rarity of Earth-like planets and the observational bias of our current detection methods, which more easily find large planets close to their stars. The habitable zone itself varies dramatically depending on the type of star. Around our Sun, this zone extends roughly from the orbit of Venus to the orbit of Mars, though the exact boundaries depend on atmospheric composition and other factors. For smaller, cooler red dwarf stars, the habitable zone lies much closer to the star. For larger, hotter stars, it extends much farther out. Recent discoveries have identified several particularly intriguing candidates for Earth-like worlds. Gliese 12b, located about 40 light-years from Earth, appears to be similar in size to Venus, but orbiting in its star's habitable zone with estimated surface temperatures that might allow liquid water. The planet completes its orbit every 12.8 days around a red dwarf star, receiving similar amounts of energy from its star as Earth receives from the Sun. Another fascinating system is TRAPPIST-1, located 39 light-years away, which hosts 7 Earth-sized rocky planets. 4 of these worlds orbit within distances where temperatures might be suitable for liquid water, creating a system with multiple potentially habitable worlds. However, recent observations with the James Webb Space Telescope have begun to reveal the challenges these planets face, including the loss of their atmospheres due to intense radiation from their host star. These discoveries illustrate both the promise and the complexity of finding truly Earth-like worlds. Being in the right orbital zone is just the beginning of habitability. A planet also needs the right atmospheric composition to maintain liquid water, protection from harmful radiation, and geological activity to recycle carbon and maintain stable surface conditions over billions of years. The atmospheric analysis of exoplanets represents one of the most exciting frontiers in astronomy today. By studying the light that passes through a planet's atmosphere during transit, we can identify the chemical fingerprints of various molecules. Water vapor, carbon dioxide, methane, and oxygen all leave distinct signatures that our instruments can detect and measure. This capability opens the possibility of identifying biosignatures, chemical indicators that might suggest the presence of life. Oxygen, for example, is so reactive that it would quickly disappear from an atmosphere unless something were continuously producing it. On Earth, that something is photosynthesis by plants and other organisms. Finding oxygen in another planet's atmosphere, especially in combination with water vapor and other gases, could indicate that life has taken hold on that distant world. The search for these atmospheric signatures has already begun, revealing surprises that challenge our assumptions about planetary atmospheres and their stability over time. As you rest peacefully, astronomers are using the James Webb Space Telescope to peer into the thin shells of gas surrounding distant worlds, reading their chemical stories like pages in a cosmic library. Each observation teaches us something new about how atmospheres form, evolve, and sometimes disappear entirely. Some planets that appeared promising from a distance have revealed themselves to be airless rocks, their atmospheres stripped away by the intense radiation of their parent stars. Others surprise us with thick, complex atmospheric layers that might create greenhouse effects strong enough to warm their surfaces, beyond what their orbital distance alone would suggest. The James Webb Telescope represents a quantum leap in our ability to study these distant atmospheres. Where previous instruments could only detect the largest atmospheric components, Webb can identify trace gases that might indicate geological activity or even biological processes. Water vapor, carbon dioxide, methane, sulfur compounds, and dozens of other molecules each leave their unique fingerprints in the starlight that filters through planetary atmospheres. This spectroscopic detective work requires extraordinary patience and precision. A single atmospheric analysis might require dozens of observations as a planet repeatedly transits its star, with each transit providing a few hours of data that must be carefully calibrated and analysed. The process is methodical, gentle, and deeply collaborative, with research teams spending months or years extracting meaningful information from these whispered signals from across the galaxy. As we learn more about atmospheric diversity, we're beginning to understand how many factors influence a planet's ability to maintain the conditions necessary for liquid water. The mass of the planet affects its ability to hold onto an atmosphere through gravitational attraction. Too small, like Mars, and the atmosphere slowly leaks away into space. Too large, and the planet might accumulate a thick hydrogen atmosphere that creates crushing surface pressures. The composition of the atmosphere matters enormously as well. Carbon dioxide acts as a greenhouse gas, trapping heat and warming the surface. Water vapor amplifies this effect, creating feedback loops that can either stabilize temperatures or drive them to extremes. Ozone in the upper atmosphere shields the surface from harmful ultraviolet radiation, while clouds can either reflect heat away from the planet or trap it close to the surface. The host star plays a crucial role in atmospheric evolution over billions of years. Young stars are often more active, producing intense flares of radiation and charged particles that can strip away planetary atmospheres. Red dwarf stars, while long-lived, can be particularly violent in their youth, potentially rendering nearby planets uninhabitable even if they later settle into calmer behavior. Our own Sun provides an example of relatively stable stellar behavior, though it too has evolved significantly over Earth's history. 4.5 billion years ago, the Sun was about 30% dimmer than it is today, yet Earth remained warm enough for liquid water thanks to a thicker carbon dioxide atmosphere that has since been largely absorbed into rocks and oceans through geological processes. This delicate balance between stellar evolution and atmospheric composition helps explain why potentially habitable planets might be rarer than simple orbital mechanics would suggest. A world might spend billions of years in its star's habitable zone, but if its atmosphere is gradually stripped away, or if geological processes fail to regulate surface temperatures, it could become uninhabitable despite maintaining the correct distance from its star. Recent studies of red dwarf planetary systems have revealed particular challenges for maintaining habitable conditions around these common but temperamental stars. Observations of nearby red dwarfs show that many produce powerful stellar flares that can increase their brightness by factors of hundreds or even thousands in a matter of minutes. These energetic outbursts bombard nearby planets with intense radiation that could not only strip away atmospheric gases, but also break apart complex molecules necessary for life. However, the story of red dwarf habitability is still being written, with new research suggesting that some of these concerns might be less severe than initially feared. Planets with strong magnetic fields might deflect much of the harmful radiation, while thick atmospheres could absorb and redistribute the energy from stellar flares. The orientation of the stellar magnetic field might also play a role, with some models suggesting that flares typically originate near the star's poles rather than its equator, potentially leaving planets in equatorial orbits relatively protected. The question of atmospheric retention around red dwarfs has become one of the most active areas of exoplanet research. Computer models suggest that planets need atmospheres perhaps 10 to 1,000 times denser than Earth's to survive the radiation environment around an active red dwarf. While this might sound prohibitive, we're learning that planetary atmospheres can be surprisingly resilient, with volcanic outgassing and other geological processes potentially replenishing gases lost to space. As you breathe slowly and let these cosmic thoughts drift through your consciousness, consider that we're still in the earliest stages of understanding planetary habitability. The first exoplanet around a Sun-like star was discovered less than 30 years ago, and our ability to study their atmospheres in detail has existed for less than a decade. Each new observation refines our understanding and often reveals unexpected complexity in how planets form, evolve, and maintain their environments over cosmic time. The diversity of planetary systems continues to surprise and delight astronomers. We've discovered planets orbiting pairs of stars, creating worlds where beings on the surface would witness spectacular double sunsets. We've found planets with orbits so eccentric that they experience extreme seasonal variations as they swing from scorching proximity to their star to frigid distances farther than Mars orbits our Sun. Some planetary systems appear to be arranged in precise mathematical relationships, with orbital periods that form simple ratios suggesting gravitational interactions that have persisted for billions of years. Others show signs of dramatic evolutionary histories, with planets that may have migrated inward from the cold outer regions of their systems, or been scattered into unusual orbits by gravitational encounters with stellar companions. The TRAPPIST-1 system provides a particularly fascinating case study in planetary system architecture and evolution. Its 7 Earth-sized planets are arranged in a compact configuration that would fit entirely within Mercury's orbit around our Sun. Despite this crowded arrangement, the planets have maintained stable orbits for what is likely billions of years, locked in a complex gravitational dance that keeps their relative positions precisely coordinated. Recent observations of TRAPPIST-1 planets have begun to reveal the individual characteristics of each world. The innermost planets appear to have lost most or all of their atmospheres to the intense radiation of their host star, while the outermost worlds may have retained thicker atmospheric layers. Some models suggest that the middle planets in the system, those most likely to be in the habitable zone, might have moderate atmospheres that could potentially support liquid water on their surfaces. The search for atmospheric water vapor around TRAPPIST-1 planets represents one of the most sensitive tests of our current observational capabilities. Water vapor in the atmosphere of a terrestrial planet would be a strong indicator of surface oceans, though it could also suggest a runaway greenhouse effect similar to what occurred on Venus. Distinguishing between these scenarios requires careful analysis of atmospheric composition and structure. As we extend our gaze beyond individual planetary systems, the statistical picture of planetary abundance becomes both humbling and inspiring. Current surveys suggest that virtually every star in our galaxy hosts at least one planet, with many stars hosting multiple worlds. This universality of planetary systems implies that the processes that form planets are robust and efficient, occurring naturally as stars condense from interstellar gas and dust. The size distribution of planets reveals interesting patterns that help us understand formation processes and estimate the abundance of potentially habitable worlds. There appears to be a gap in the size distribution between planets, about 1.5 times Earth's size, and those about twice Earth's size. This gap might represent a fundamental transition between rocky planets that can hold onto thin atmospheres and larger worlds that accumulate thick gaseous envelopes. Planets smaller than this transition size, often called super-Earths, are among the most common planetary types discovered by our surveys. These worlds, larger than Earth but smaller than Neptune, have no direct analogues in our solar system, making their properties and potential habitability subjects of intense study and speculation. Some super-Earths might be essentially scaled-up versions of Earth, with thicker atmospheres and stronger surface gravity, but otherwise similar conditions. Others might be more like mini-Neptunes, with thick hydrogen atmospheres that create crushing surface pressures and temperatures. The boundary between these two possibilities appears to depend on the planet's formation history, its distance from its star, and the timing of atmospheric loss processes during its early evolution. The abundance of super-Earths in our galaxy suggests that Earth-sized planets represent just one point on a continuum of potentially habitable world types. If super-Earths can maintain temperate surface conditions, the number of potentially habitable worlds in our galaxy could be significantly larger than estimates based solely on Earth-sized planets. Current statistical analyses of exoplanet surveys suggest that somewhere between 5 and 20% of Sun-like stars host potentially habitable planets within a factor of 2 of Earth's size. For red dwarf stars, which make up about 75% of all stars in our galaxy, the estimates range from 10 to 50%, though the challenges of maintaining habitable conditions around these active stars remain uncertain. When we multiply these percentages by the estimated 100 to 400 billion stars in our galaxy, we arrive at estimates of billions to tens of billions of potentially habitable worlds in the Milky Way alone. These numbers represent our best current understanding based on limited observational data and they will certainly be refined as we discover and characterize more planetary systems. The uncertainty in these estimates reflects both the limitations of our current surveys and the complexity of defining habitability. Our telescopes are most sensitive to planets that orbit close to their stars and transit frequently, creating observational biases that we must carefully account for when extrapolating to the entire galactic population. Future space missions promise to reduce these uncertainties by directly imaging Earth-like planets around nearby stars and analyzing their atmospheric compositions in detail. The proposed Habitable Worlds Observatory would be specifically designed to detect and characterize potentially habitable planets, providing the first census of truly Earth-like worlds in our galactic neighborhood. As you continue to rest comfortably, breathing slowly, and letting your mind drift among these countless distant worlds, consider that we exist at a unique moment in human history. For the first time, we possess the technology to detect and study planets orbiting other stars, to analyze their atmospheric compositions, and to begin answering the ancient question of whether Earth-like conditions exist elsewhere in the universe. This capability has developed remarkably quickly, accelerating from the first tentative detections of massive planets in the 1990s to today's sophisticated atmospheric analyses of terrestrial worlds. The pace of discovery continues to accelerate as new missions launch and observational techniques improve, suggesting that the coming decades will bring unprecedented insights into the abundance and diversity of potentially habitable worlds. Each confirmed exoplanet represents a triumph of human ingenuity, international collaboration, and patient observation. The signals we detect are incredibly subtle, often requiring years of careful measurement and analysis to confirm. The process demands not just advanced technology, but also the careful application of physics, chemistry, and statistics to extract reliable information from these faint cosmic whispers. The search for Earth-like planets also represents one of the most profound scientific questions we can ask about our place in the universe. If Earth-like conditions are common, it suggests that life might be abundant throughout the galaxy, perhaps even inevitable given sufficient time and appropriate conditions. If Earth-like conditions are rare, it emphasizes the precious nature of our own world and the responsibility we bear as possibly one of the few intelligent species in our galactic neighborhood. Current evidence suggests that the answer lies somewhere between these extremes. Rocky planets appear to be common, and many orbit within their stars' habitable zones. However, the additional requirements for maintaining stable, habitable conditions over billions of years appear to impose significant additional constraints that may render truly Earth-like worlds relatively uncommon. The ongoing characterization of planetary atmospheres will help resolve this question by revealing which potentially habitable worlds have actually maintained the conditions necessary for liquid water and stable surface environments. These observations will also help us understand the range of atmospheric compositions and surface conditions that might support life, potentially expanding our definition of habitability beyond strictly Earth-like parameters. As we peer deeper into space with increasingly sophisticated instruments, we're beginning to assemble a census of our galactic neighbors that would have seemed like pure fantasy just a generation ago. We can now detect planets orbiting stars hundreds of light years away, analyze the chemical composition of their atmospheres, and begin to assess their potential for harboring the conditions necessary for life as we understand it. This expanding catalogue of distant worlds serves as both a scientific treasure trove and a source of philosophical reflection on the nature of existence itself. Each planet represents a unique experiment in cosmic evolution, a world where the fundamental laws of physics and chemistry have played out over billions of years to create conditions we're only beginning to understand. The gentle rhythm of these discoveries, each building upon previous observations and theoretical understanding, reflects the patient and methodical nature of modern astronomy. Unlike the dramatic revelations often portrayed in science fiction, real astronomical discovery proceeds through careful accumulation of evidence, peer review, and gradual refinement of our understanding. This measured approach ensures that when we speak of potentially habitable worlds, We're discussing genuine scientific conclusions based on observable evidence rather than speculation or wishful thinking. The thousands of confirmed exoplanets in our current catalogues represent real worlds, each with measured properties that place meaningful constraints on their possible characteristics and habitability. The gentle precision required for these measurements reflects the extraordinary sensitivity of our modern astronomical instruments. When we observe the subtle dimming of starlight as a planet passes between its star and our telescopes, we are detecting changes so minute they would be like noticing the shadow of a penny held up against a lighthouse beam from 50 miles away. Yet our instruments perform this delicate work night after night, accumulating the patient observations that slowly reveal the hidden architecture of distant planetary systems. This process of discovery unfolds at a pace that mirrors the cosmic rhythms we study. A single planet confirmation might require years of repeated observations, mathematical analysis, and careful verification by multiple research teams around the world. There's something deeply peaceful in this methodical approach, this gradual accumulation of knowledge that builds our understanding, one careful measurement at a time. The stars themselves provide the foundation for all planetary discovery. Our galaxy, the Milky Way, contains an estimated 100 to 400 billion stars, each one a potential host for planetary companions. This vast stellar population represents the basic framework within which we search for Earth-like worlds, though the actual number remains beautifully uncertain, reminding us of the limits of human knowledge even as our understanding expands. These stellar estimates come from careful surveys of nearby regions of our galaxy, combined with mathematical models that extrapolate these local measurements to the entire galactic disk. The uncertainty in these numbers reflects both the challenges of counting objects across such vast distances and the complex structure of our galaxy, with its spiral arms, central bulge, and sparse outer regions, each contributing different stellar populations to the total. The diversity of stars within this vast collection plays a crucial role in determining how many potentially habitable worlds might exist. Our Sun belongs to a class of stars known as G-type dwarfs, medium-sized stars that burn their nuclear fuel at a steady rate for approximately 10 billion years. These Sun-like stars make up only about 5% of all stars in our galaxy, yet they may provide the most stable environments for the long-term evolution of life. More numerous are the red dwarf stars, smaller and cooler than our Sun, which comprise roughly 3/4 of all galactic stars. These diminutive stellar furnaces burn their fuel so efficiently that they can shine for hundreds of billions of years, providing potential energy sources that would outlast our Sun by factors of 10 or more. However, as we've gently explored, planets around red dwarfs face unique challenges that may complicate their habitability. The remaining stellar population includes larger, hotter stars that burn brilliantly but briefly, massive stellar giants that may not live long enough for complex life to evolve on their planets, and the exotic remnants of dead stars that present their own fascinating but likely sterile environments for any surviving planetary companions. When we consider the broader cosmic context, the scale becomes even more breathtaking. Our Milky Way galaxy is just one among an estimated 2 trillion galaxies in the observable universe. Each of these galactic islands contains its own vast collection of stars and, by extension, planets. The numbers become so large that they transcend easy comprehension, entering realms where mathematics provides our only reliable guide through the cosmic immensity. Yet even these staggering galactic numbers represent only what we can observe from our current vantage point in space and time. The observable universe extends only as far as light has had time to travel since the cosmic beginning, roughly 14 billion years ago. Beyond this observational horizon lies an unknown expanse that may contain countless additional galaxies, each hosting their own stellar and planetary populations. This expanding perspective reminds us that when we ask how many Earths could exist right now, we're really exploring multiple nested questions about stellar populations, planetary formation rates, and the specific conditions required for Earth-like habitability. Each level of this cosmic hierarchy contributes uncertainty to our final estimates, creating ranges rather than precise numbers. Current observational data suggests that rocky planets are remarkably common throughout our galaxy. Surveys from the Kepler Space Telescope and its successors indicate that most stars host at least one planet, with many systems containing multiple worlds. Among these planetary populations, rocky planets similar in size to Earth appear to form frequently, though they represent just one category within the broader spectrum of planetary types. The size distribution of discovered exoplanets reveals interesting patterns that help us understand both formation processes and observational limitations. Earth-sized planets are relatively challenging to detect with current techniques, requiring multiple transits and careful analysis to distinguish their subtle signals from instrumental noise and stellar variability. Larger planets create more pronounced signals that are easier to detect and confirm, potentially biasing our current catalogues toward worlds that may be quite different from Earth. Super-Earth planets, with sizes between 1 and 2 times Earth's radius, appear to be among the most common planetary types in our galaxy. These intermediate-sized worlds have no direct analogues in our own solar system, making their properties and potential habitability subjects of ongoing research and theoretical modelling. Some may be scaled-up versions of Earth with thicker atmospheres and higher surface gravity. Others might be more like stripped-down versions of Neptune, with residual gaseous envelopes that create very different surface conditions. The boundary between rocky super-Earths and mini-Neptune planets appears to occur around twice Earth's radius, representing a fundamental transition in planetary composition and structure. Understanding this transition helps astronomers estimate what fraction of discovered planets might have solid surfaces and potentially habitable environments. Though many questions remain about the atmospheric and surface conditions of these intermediate-sized worlds. When we focus specifically on the subset of rocky planets that orbit within their star's habitable zone, the numbers become more manageable, but also more uncertain. Current estimates suggest that somewhere between 5 and 20% of Sun-like stars host rocky planets within the temperature range, where liquid water could exist on their surfaces. This wide range reflects both the limitations of current surveys and the ongoing debates about the exact boundaries of habitable zones around different types of stars. For red dwarf stars, which dominate the galactic stellar population, the estimates for habitable zone planets range even more widely, from 10 to 50%, depending on how we account for the unique challenges these systems present. The uncertainty here reflects our still developing understanding of atmospheric retention, stellar activity, and tidal effects in these compact planetary systems. Multiplying these percentages by the estimated stellar populations in our galaxy produces ranges of potentially habitable worlds that span from hundreds of millions to tens of billions. These vast numbers represent our best current understanding, though they will certainly be refined as our observational capabilities improve and our theoretical understanding deepens. The Drake equation, formulated by astronomer Frank Drake in 1961, provides a framework for thinking about these cosmic numbers in the context of life and intelligence. This mathematical expression breaks down the question of extraterrestrial intelligence into component factors, including star formation rates, the fraction of stars with planets, the number of habitable worlds per system, and the likelihood that life will develop and become detectable. While the Drake equation cannot provide definitive answers given our current knowledge, it serves as a useful tool for organizing our thinking about the factors that influence the abundance of life in the universe. Each term in the equation represents an area of active research, from planetary formation and atmospheric evolution to astrobiology and the search for biosignatures in exoplanet atmospheres. Recent advances in exoplanet detection and characterization have begun to constrain some terms in the Drake equation with observational data, rather than pure speculation. We now know that planets are common, that rocky worlds form frequently, and that many orbit within potentially habitable zones. However, the biological terms in the equation remain largely unknown, representing perhaps the greatest uncertainties in estimating the cosmic abundance of life. The question of how common life might be touches on some of the deepest mysteries in science. We have only one example of life here on Earth, making it difficult to assess whether biological processes are rare cosmic accidents or inevitable consequences of appropriate chemical conditions. Recent discoveries of potentially habitable environments within our own solar system, including subsurface oceans on moons like Europa and Enceladus, suggest that the requirements for life might be less restrictive than previously thought. However, the emergence of complex life, and especially intelligent life capable of technology and communication, may face additional bottlenecks that could make such phenomena much rarer than simple microbial life. The evolution of complex cells, multicellular organisms, and eventually intelligence may each represent low-probability transitions that occurred on Earth, but might be uncommon elsewhere. These considerations remind us that finding a planet in the habitable zone of its star represents just the first step in assessing its potential for life. A world must also maintain stable atmospheric conditions over billions of years, develop and sustain a magnetic field to protect against harmful radiation, and experience geological activity that recycles carbon and other essential elements through the atmosphere and oceans. The atmospheric retention problem becomes particularly acute for smaller planets and those orbiting active stars. Mars provides a sobering example within our own solar system of how a planet can lose its atmosphere over geological time, transforming from a potentially habitable world with flowing water into the cold, thin-air desert we observe today. Understanding atmospheric evolution requires detailed knowledge of planetary interiors, magnetic field generation, stellar activity levels, and the complex interactions between rocks, oceans, and atmospheric gases. These processes operate over timescales of millions to billions of years, making them challenging to study directly, but crucial for assessing long-term habitability. Recent atmospheric observations of exoplanets have begun to reveal the diversity of possible atmospheric compositions and structures around other stars. Some worlds appear to have retained thick atmospheres despite intense stellar radiation, while others have been stripped nearly bare. These observations provide crucial data for understanding which types of planets can maintain habitable conditions over cosmic time. The James Webb Space Telescope has revolutionized our ability to study exoplanet atmospheres, revealing molecular compositions with unprecedented detail and precision. Water vapor, carbon dioxide, methane, and other atmospheric constituents leave distinct spectroscopic signatures that allow us to map the chemical environments of distant worlds from across interstellar space. These atmospheric studies have already revealed surprises that challenge our theoretical understanding. Some planets show evidence for thick clouds that could dramatically affect surface temperatures. Others display unusual chemical compositions that suggest active geological processes, or possibly even biological activity, though distinguishing between geological and biological sources of atmospheric gases remains a significant challenge. The search for biosignatures in exoplanet atmospheres represents one of the most exciting frontiers in modern astronomy. Oxygen, particularly in combination with water vapor and other gases, could indicate photosynthetic processes similar to those that transformed Earth's atmosphere billions of years ago. However, distinguishing biological from geological sources of oxygen requires careful analysis and multiple independent measurements. Methane presents another potential biosignature, though it too can be produced by both biological and geological processes. On Earth, most atmospheric methane comes from biological sources, but on other worlds, volcanic activity or chemical reactions in the atmosphere could produce similar gas concentrations without any biological involvement. The complexity of interpreting atmospheric biosignatures underscores the challenges involved in confirming the presence of life on distant worlds. Even with our most advanced instruments, we can only observe the combined effects of all processes operating on a planet, making it difficult to isolate potential biological contributions from the broader geochemical environment. Future space missions will attempt to address these challenges by observing larger samples of potentially habitable planets and developing more sophisticated techniques for atmospheric analysis. The proposed Habitable Worlds Observatory would be specifically designed to directly image Earth-like planets and analyze their atmospheric compositions with sufficient precision to search for clear biosignatures. Ground-based, extremely large telescopes currently under construction will complement space-based observations by providing high-resolution spectroscopy of the brightest exoplanet targets. These instruments will be particularly valuable for studying nearby planetary systems, where individual planets can be observed repeatedly over many years to search for seasonal variations and long-term atmospheric changes. The statistical approach to understanding planetary habitability continues to evolve as our observational databases grow larger and more complete. Each newly discovered exoplanet adds to our understanding of planetary system architectures, atmospheric retention, and the factors that influence long-term habitability. Current surveys have revealed that planetary systems show remarkable diversity in their arrangements and properties. Some systems contain multiple rocky planets packed into tight orbits around their host stars. Others feature widely separated worlds with eccentric orbits that carry them through dramatic temperature variations. Still others show evidence for dramatic evolutionary histories, with planets that may have migrated substantial distances from their formation locations. This diversity suggests that there may be many different pathways to habitability, with some planetary configurations offering advantages that compensate for apparent disadvantages. Planets with eccentric orbits might experience seasonal variations that help circulate heat around their surfaces. Worlds in multiple planet systems might benefit from gravitational interactions that stabilize their climates over long periods. The study of planetary system dynamics has revealed the importance of gravitational interactions in shaping long-term habitability. The presence of large planets in outer orbits can protect inner worlds from cometary impacts that might otherwise disrupt the development of life. Conversely, giant planets in unstable orbits could scatter smaller worlds into uninhabitable regions or strip away their atmospheres through close gravitational encounters. Our own solar system provides examples of how planetary interactions can both help and hinder habitability. Jupiter's massive gravitational influence has likely protected Earth from frequent large impacts while also helping to deliver water and organic compounds during the early stages of planetary formation. However, Jupiter's migration during the solar system's youth may have also prevented the formation of additional rocky planets in what is now the asteroid belt. These complex dynamics remind us that assessing planetary habitability requires understanding not just individual world properties, but entire system architectures and their evolutionary histories. A planet that appears habitable in isolation might face challenges from gravitational perturbations, impact bombardment, or other system-wide effects that could compromise its long-term stability. The temporal dimension of habitability adds another layer of complexity to our estimates of potentially life-bearing worlds. A planet might spend only a fraction of its orbital evolution within its star's habitable zone, as stellar brightness changes over billions of years. Alternatively, atmospheric evolution might cause a world to lose its habitability even while remaining at the optimal distance from its star. Earth itself provides an example of how planetary habitability can evolve over cosmic time. Our planet has experienced dramatic climate variations, mass extinction events, and fundamental changes in atmospheric composition while maintaining the basic conditions necessary for life. Understanding which factors have allowed Earth to remain habitable for nearly 4 billion years helps us assess the likelihood that other worlds could achieve similar stability. The concept of a continuously habitable zone attempts to account for stellar evolution by identifying orbital distances where planets could maintain liquid water throughout their star's main sequence lifetime. This approach tends to produce more restrictive estimates of habitable real estate, as it requires planets to remain within the relatively narrow zone of optimal temperatures for billions of years as their host stars gradually brighten. Climate modelling studies suggest that planets with active carbon cycles might be able to regulate their surface temperatures over long periods by adjusting atmospheric carbon dioxide concentrations in response to changing stellar brightness. This planetary thermostat effect could significantly expand the range of orbits where long-term habitability is possible, though it requires geological activity and surface water to operate effectively. The role of planetary mass in maintaining habitable conditions over geological timescales represents another active area of research. More massive planets can retain their atmospheres more easily and may sustain geological activity for longer periods, but they also experience stronger surface gravity that could affect atmospheric circulation and ocean dynamics in ways that remain poorly understood. Tidal heating provides an alternative energy source that could maintain habitable conditions on planets orbiting close to their host stars or in eccentric orbits around more distant stars. This gravitational energy source could drive geological activity and atmospheric circulation even on worlds that receive minimal energy from stellar radiation, potentially expanding the range of environments where life could persist. The moons of giant planets represent another category of potentially habitable worlds that might not be captured in traditional estimates based on stellar habitable zones. Large moons could maintain their own magnetic fields and geological activity while orbiting within the gravitational influence of massive planets that provide additional energy sources through tidal heating. Our own solar system contains several examples of potentially habitable moons, including Europa, Enceladus, and possibly Titan, which maintains subsurface oceans despite receiving minimal energy from the Sun. If similar moon systems are common around other stars, the total number of potentially habitable environments in our galaxy could be substantially larger than estimates based solely on planets in stellar habitable zones. The detection and characterization of exomoons remains beyond our current observational capabilities, though future missions may be able to identify the largest moons around nearby exoplanets. These observations could reveal whether moon systems are common and whether they might contribute significantly to the galactic population of potentially habitable environments. As we continue this gentle exploration of cosmic possibilities, the numbers we encounter become both more precise and more uncertain with each new discovery. Current estimates suggest that our galaxy contains billions of rocky planets, hundreds of millions of worlds in stellar habitable zones, and perhaps tens of millions of planets with stable, long-term conditions suitable for the development and evolution of life. These estimates span enormous ranges because they depend on many factors that remain poorly understood. The efficiency of atmospheric retention around different types of stars, the role of magnetic fields in protecting planetary environments, the importance of geological activity in maintaining climate stability, and the probability of developing self-regulating climate systems all influence the final numbers but remain active areas of research. The philosophical implications of these estimates range from profound loneliness to cosmic abundance. If Earth-like conditions are genuinely rare, occurring on only 1 in a million or 1 in a billion otherwise suitable planets, then our world becomes precious beyond measure, possibly unique in our galactic neighborhood and deserving of extraordinary care and protection. Alternatively, if Earth-like conditions develop readily given appropriate circumstances, then our galaxy might host millions or billions of worlds where life has taken hold and evolved over cosmic timescales. In such a universe, Earth would represent just one example among many of life's remarkable ability to emerge and flourish given suitable conditions. Current evidence suggests that the truth likely lies somewhere between these extremes. Rocky planets appear common, and many orbit within zones where liquid water could exist. However, the additional requirements for maintaining stable, habitable conditions over billions of years may impose significant constraints that render truly Earth-like worlds relatively uncommon, while still allowing for substantial numbers across our galaxy's vast stellar population. The ongoing characterization of exoplanet atmospheres will help refine these estimates by revealing which potentially habitable worlds have actually maintained the conditions necessary for surface water and stable climates. These observations will also help us understand the range of atmospheric compositions and planetary characteristics that might support life, potentially expanding our definition of habitability beyond strictly Earth-like parameters. As you rest peacefully and let these vast numbers drift gently through your consciousness, consider that we're witnessing the emergence of a new kind of cosmic census. For the first time in human history, we're beginning to count not just stars and galaxies, but the actual worlds that orbit those distant suns, measuring their sizes and temperatures, analyzing their atmospheric compositions, and assessing their potential for harboring the conditions that gave rise to life on our own precious planet. This expanding catalogue of distant worlds serves as both a scientific achievement and a source of wonder about our place in the cosmic order. Each discovered planet represents a unique experiment in planetary formation and evolution, a world where the fundamental laws of physics and chemistry have operated over billions of years to create conditions we're only beginning to understand. The gentle rhythm of these discoveries, accumulating night after night as our telescopes scan the heavens, reflects the patient and methodical nature of modern astronomical research. Unlike the dramatic revelations often imagined in science fiction, real astronomical discovery proceeds through careful observation, mathematical analysis, and gradual refinement of our understanding of how planetary systems form and evolve. This measured approach ensures that when we speak of potentially Earth-like worlds, we're discussing genuine scientific conclusions based on measurable evidence rather than speculation or wishful thinking. The thousands of confirmed exoplanets in our current databases represent real worlds with measured properties that constrain their possible characteristics and habitability. The uncertainty inherent in extrapolating from these observations to galactic populations reflects the honest limitations of human knowledge rather than any failure of scientific method. We observe only the nearest fraction of our galaxy's stellar population, detect only the most easily observable planetary systems, and analyze atmospheres only for the most favorable targets. Acknowledging these limitations allows us to express our current understanding as ranges of possibility rather than false precision. Future observations will undoubtedly refine these estimates, potentially revealing that Earth-like worlds are more common than current data suggests, or alternatively, that the additional requirements for long-term habitability make such worlds rarer than optimistic projections indicate. Either outcome would represent genuine progress in understanding our cosmic neighborhood and our place within it. The search for Earth-like planets continues to accelerate as new missions launch and observational techniques improve. Each technological advance expands our ability to detect smaller planets, analyze fainter atmospheric signals, and characterize worlds around a broader range of stellar types. This expanding capability suggests that the coming decades will bring unprecedented insights into the abundance and diversity of potentially habitable worlds. As you breathe slowly and deeply, letting your mind drift among these countless distant possibilities, you're participating in one of humanity's greatest adventures of exploration and discovery. We may never travel to these distant worlds, but through the patient application of physics and mathematics, we can learn about their basic properties and assess their potential for harboring the chemical processes that gave rise to life on Earth. The gentle precision of these measurements connects us across vast distances to worlds that may be remarkably similar to our own, spinning quietly through space with their own cycles of day and night, their own weather patterns and seasonal variations, perhaps their own complex chemistry of life and evolution. Or they may be utterly alien, with atmospheric compositions and surface conditions unlike anything in our experience. reminding us of the remarkable diversity that emerges from the simple laws that govern planetary formation and evolution. In either case, these distant worlds expand our perspective on the possible and help us appreciate both the apparent rarity of Earth-like conditions and the vast scale on which the universe operates. Whether Earth proves to be unique or merely one example among billions of life-bearing worlds, the search itself enriches our understanding of the cosmos and our place within its magnificent complexity. The question of how many Earths could exist right now ultimately leads us to contemplate the nature of existence itself, the delicate balance of conditions that allows for the emergence of complexity and consciousness in a universe governed by fundamental physical laws. As you rest comfortably in the knowledge that science continues this gentle exploration, you can take comfort in knowing that each new discovery adds to humanity's growing understanding of the cosmic environment that gave rise to our own remarkable planet and all the life it sustains. The delicate dance of planetary formation around red dwarf stars reveals patterns that continue to surprise astronomers with their subtle complexity. As you settle deeper into rest, imagine the slow gravitational ballet that creates these compact planetary systems, where worlds orbit so close to their dim stellar companions that a single year might last only a few Earth days. Recent computer simulations suggest that planets forming around red dwarfs experience a fundamentally different evolutionary pathway than those in systems like our own. The protoplanetary disks of gas and dust around these small stars extend inward, much closer to the stellar surface, allowing rocky planets to accumulate material in regions that would be far too hot around a sun-like star. This process creates planetary systems that are compressed versions of more familiar architectures, with multiple Earth-sized worlds packed into orbital spaces smaller than Mercury's path around our Sun. The gravitational interactions within these compact systems often lead to remarkable orbital synchronizations known as resonant chains. In the TRAPPIST-1 system, for example, the 7 planets have settled into precise mathematical relationships where their orbital periods form simple ratios. The innermost planet completes exactly 8 orbits for every 5 orbits of the second planet, which completes 5 orbits for every 3 of the third planet, and so on throughout the system. These resonant configurations represent a kind of cosmic harmony that emerges naturally from millions of years of gravitational fine-tuning. As the planets slowly migrate through their protoplanetary disk during formation, they become trapped in these stable mathematical relationships that persist for billions of years. The precision required for such synchronization speaks to the remarkable self-organizing properties of gravitational systems operating over cosmic timescales. However, this same gravitational intimacy that creates such elegant orbital arrangements also poses challenges for maintaining habitable conditions. Planets in these compact systems experience tidal forces from their star and neighboring worlds that can dramatically affect their internal structure and atmospheric evolution. The constant gravitational kneading heats planetary interiors, potentially driving geological activity for much longer periods than isolated worlds might sustain. Tidal heating represents both an opportunity and a challenge for habitability around red dwarf stars. The steady input of gravitational energy could maintain liquid water on planets that would otherwise be too cold, extending the effective habitable zone outward from what stellar radiation alone would suggest. However, excessive tidal heating could also drive away atmospheric water through enhanced volcanic outgassing or create surface conditions too extreme for life as we understand it. The phenomenon of tidal locking adds another layer of complexity to red dwarf planet habitability. Most planets orbiting within the habitable zones of these small stars likely show the same face to their star at all times, creating permanent day and night hemispheres with extreme temperature contrasts. The day side might experience scorching temperatures where any water boils away, while the night side could be cold enough to freeze carbon dioxide from the atmosphere. Yet atmospheric circulation models suggest that thick atmospheres might redistribute heat efficiently enough to moderate these temperature extremes, Computer simulations indicate that planets with atmospheric pressures several times greater than Earth's could transport warm air from their day sides to their night sides, creating temperate zones near the terminator regions, where eternal twilight might support liquid water and stable surface conditions. The question of atmospheric retention around red dwarf stars remains one of the most active areas of current research. Early theoretical models suggested that the intense radiation and stellar winds from young red dwarfs would strip away planetary atmospheres within hundreds of millions of years. However, more recent studies indicate that this process might be less efficient than initially feared, particularly for planets with strong magnetic fields or dense initial atmospheres. Observations with the James Webb Space Telescope have begun to test these theoretical predictions by analyzing the current atmospheric properties of red dwarf planets. The results so far present a mixed picture, with some planets showing evidence of substantial atmospheric loss, while others appear to have retained significant gaseous envelopes despite billions of years of stellar bombardment. The TRAPPIST-1 system has become a natural laboratory for studying atmospheric evolution around red dwarfs. Recent observations suggest that the innermost planets have indeed lost most of their original atmospheres, while the outer worlds may have retained thicker atmospheric layers. This gradient of atmospheric retention provides valuable constraints on theoretical models and helps astronomers understand which factors most strongly influence long-term habitability. The discovery of atmospheric water vapor around any TRAPPIST-1 planet would represent a major milestone in exoplanet science, as it would indicate not only atmospheric retention, but also the potential presence of surface oceans. However, detecting water vapor requires extremely sensitive measurements that push current observational capabilities to their limits, requiring multiple observations over many months to achieve sufficient precision. Beyond individual planetary systems, the broader statistics of red dwarf planet populations continue to evolve as survey data accumulates. The Transiting Exoplanet Survey satellite has identified thousands of candidate planets around nearby red dwarfs, providing the large sample sizes needed to assess how common potentially habitable worlds might be around these ubiquitous stellar neighbors. Current statistical analyses suggest that roughly 20 to 50% of red dwarf stars may host rocky planets within their habitable zones. However, the fraction of these planets that actually maintain habitable surface conditions over billions of years remains highly uncertain, with estimates ranging from less than 1% to more than half, depending on assumptions about atmospheric retention, magnetic field generation, and stellar activity levels. The abundance of red dwarf stars in our galaxy means that even conservative estimates of their habitability rates translate into substantial numbers of potentially life-bearing worlds. With perhaps 75 billion red dwarfs in the Milky Way, even if only 1% host truly habitable planets, that would still represent hundreds of millions of worlds where life might have gained a foothold. These numerical estimates take on additional significance when we consider the extreme longevity of red dwarf stars. While our Sun will exhaust its nuclear fuel in approximately 5 billion years, red dwarfs can continue shining for hundreds of billions of years, providing stable energy sources that far outlast the current age of the universe. Any life that does establish itself around these diminutive stars would have vast periods of time available for evolution and development. The extended lifespans of red dwarf stars also mean that the youngest examples are still settling into their mature, less active phases. Many red dwarfs that are currently too active to support nearby habitable planets may become suitable hosts for life in the future as their stellar magnetic fields weaken and their radiation output stabilizes. This temporal evolution suggests that the galactic population of habitable worlds may continue growing for hundreds of billions of years. As you breathe slowly and let these temporal perspectives wash over your consciousness, consider the remarkable patience required for studying stellar and planetary evolution. The processes that determine long-term habitability operate over timescales that dwarf human civilization, requiring scientists to piece together evolutionary stories from snapshots of different systems at various stages of development. Computer models play an essential role in bridging these vast temporal gaps, allowing researchers to simulate billions of years of atmospheric evolution, stellar activity, and planetary climate dynamics. These numerical experiments reveal the intricate feedback loops between stellar radiation, atmospheric chemistry, and surface geology that ultimately determine whether a world can maintain habitable conditions over cosmic time. The results of these modelling efforts often challenge our intuitive expectations about planetary habitability. Worlds that appear promising based on their orbital distance and size sometimes prove vulnerable to atmospheric loss or climate instability when their full evolutionary histories are considered. Conversely, planets that seem marginal based on simple criteria occasionally emerge as surprisingly robust when their complex climate systems are modelled in detail. Venus provides a sobering example within our own solar system of how apparently Earth-like conditions can evolve toward uninhabitable extremes. Despite receiving only twice as much solar energy as Earth, Venus developed a runaway greenhouse effect that created surface temperatures hot enough to melt lead. Understanding how and why Venus diverged so dramatically from Earth's evolutionary path helps astronomers identify similar risks for exoplanets orbiting closer to their stars. The atmospheric composition of Venus reveals the end result of uncontrolled greenhouse warming, with surface pressures 90 times greater than Earth's and an atmosphere composed almost entirely of carbon dioxide. Sulfuric acid clouds perpetually shroud the planet, creating an environment so extreme that even robotic spacecraft survive only hours on the surface before succumbing to the crushing pressure and corrosive chemistry. Mars represents the opposite extreme, demonstrating how planets can lose their atmospheres and become too cold to support liquid water on their surfaces. Geological evidence indicates that ancient Mars once hosted flowing rivers, standing lakes, and possibly even oceans, but its thin current atmosphere creates surface conditions where liquid water cannot persist except under very specific circumstances. The evolutionary stories of Venus and Mars highlight the narrow range of conditions that allow planets to maintain stable, temperate climates over geological time. Earth's successful navigation of this middle path required a fortunate combination of planetary mass, atmospheric composition, magnetic field strength, and orbital characteristics that may be less common than simple habitable zone calculations would suggest. These examples from our own solar system inform our assessment of exoplanet habitability by demonstrating the many ways planetary climates can evolve away from life-friendly conditions. They also highlight the importance of factors beyond simple orbital distance, including atmospheric composition, geological activity, and magnetic field generation in determining long-term habitability. The search for atmospheric biosignatures on exoplanets draws inspiration from our understanding of how life has influenced Earth's atmospheric composition over billions of years. The presence of oxygen in our atmosphere represents perhaps the most dramatic example of biological impact on planetary chemistry, as this highly reactive gas would quickly disappear without continuous replenishment by photosynthetic organisms. Early Earth's atmosphere contained virtually no free oxygen, consisting instead of methane, ammonia, and other gases produced by volcanic outgassing and impact delivery. The gradual accumulation of oxygen beginning around 2.4 billion years ago fundamentally transformed our planet's chemistry, allowing for the evolution of complex life forms that depend on oxygen-based metabolism, while also creating the ozone layer that protects Earth's surface from harmful ultraviolet radiation. This great oxidation event, as geologists call it, demonstrates how life can dramatically alter planetary environments in ways that become detectable across interstellar distances. The simultaneous presence of oxygen and water vapor in an exoplanet's atmosphere would represent a powerful biosignature, as these gases normally react with each other unless something is continuously producing fresh oxygen. However, Interpreting atmospheric biosignatures requires careful consideration of non-biological processes that might produce similar chemical signatures. Photochemical reactions driven by stellar ultraviolet radiation can split water molecules and release oxygen, potentially creating false positive biosignatures on planets where no life exists. Distinguishing between biological and abiotic sources of atmospheric gases represents one of the most challenging aspects of current exoplanet science. The James Webb Space Telescope's atmospheric observations have already revealed unexpected complexity in exoplanet atmospheric chemistry, with some worlds showing unusual compositions that challenge theoretical predictions. These discoveries underscore the importance of studying large samples of planetary atmospheres to understand the full range of possible chemical environments and identify those that might genuinely indicate biological activity. Future space missions dedicated to exoplanet characterization will expand these atmospheric studies to larger samples of potentially habitable worlds. The proposed Habitable Worlds Observatory would be specifically designed to directly image Earth-like planets around nearby Sun-like stars and analyze their atmospheric compositions with sufficient precision to search for clear biosignatures. Direct imaging of exoplanets represents an extraordinary technical challenge, requiring telescopes to block out the overwhelming brightness of host stars while detecting the faint reflected light from orbiting planets. The brightness contrast between a star and its planets can exceed 10 billion to 1, making this observation roughly equivalent to detecting a firefly next to a searchlight from thousands of miles away. Advanced coronagraph technologies currently under development will use precise optical techniques to suppress starlight while preserving the faint signals from nearby planets. These instruments will work in combination with adaptive optic systems that correct for atmospheric turbulence, creating stable enough observing conditions to detect and characterize Earth-like worlds around nearby stars. The technical requirements for direct exoplanet imaging have driven innovations in precision optics, spacecraft stability, and data analysis techniques that push the boundaries of current engineering capabilities. Success in this endeavor would open entirely new avenues for studying exoplanet atmospheres and surface properties, potentially revealing details about weather patterns, seasonal variations, and surface composition that remain inaccessible through current transit and radial velocity techniques. Ground-based, extremely large telescopes currently under construction will complement space-based direct imaging efforts by providing high-resolution spectroscopy of the brightest exoplanet targets. These massive instruments, with primary mirrors 30 to 40 meters in diameter, will collect enough light to study atmospheric chemistry in unprecedented detail for nearby planetary systems. The combination of space-based direct imaging and ground-based spectroscopic follow-up promises to revolutionize our understanding of exoplanet diversity and habitability within the next 2 decades. These observational capabilities will finally allow astronomers to move beyond statistical estimates based on limited samples toward detailed characterization of individual, potentially habitable worlds. As you rest peacefully and let your mind drift among these technological marvels, consider how each advance in observational capability brings us closer to answering fundamental questions about our place in the universe. The patient development of these precision instruments reflects humanity's deep curiosity about whether Earth-like conditions exist elsewhere and whether we are alone in the cosmic expanse. The philosophical implications of discovering life on other worlds have fascinated thinkers for centuries. But only recently have we developed the technological capability to transform these questions from pure speculation into observational science. Whether we find that life is common or rare will profoundly influence our understanding of biology, our responsibility as stewards of Earth's biosphere, and our perspective on humanity's cosmic significance. Current estimates of potentially habitable exoplanets span enormous ranges precisely because we remain in the early stages of answering these profound questions. As our observational databases grow larger and our theoretical understanding deepens, these ranges will narrow toward more precise values that better reflect the true abundance of life-friendly environments in our galaxy. The uncertainty inherent in current estimates reflects the honest limitations of human knowledge rather than any failure of scientific methodology. We observe only a tiny fraction of our galaxy's stellar population, detect only the most easily observable planetary systems, and can analyze atmospheric compositions only for the most favorable targets. Acknowledging these limitations allows us to express our current understanding appropriately, while recognizing that future discoveries may substantially revise our perspective. The exponential growth in exoplanet discoveries over the past 3 decades suggests that the coming years will bring unprecedented insights into planetary system diversity and the factors that influence habitability. Each new discovery adds to our understanding while often revealing unexpected complexity that keeps the universe interesting and surprising. The collaborative nature of modern exoplanet science, with research teams around the world sharing observations and theoretical insights, reflects the global human interest in these cosmic questions. International cooperation in space missions, data sharing between observatories, and collaborative theoretical modeling efforts demonstrate how the search for other Earths brings out the best aspects of human curiosity and cooperation. The gentle rhythm of scientific discovery in this field mirrors the cosmic processes we study. Individual planet conformations often require years of patient observation and careful analysis, building our understanding gradually through the accumulation of precise measurements and theoretical insights. There's something deeply satisfying about this methodical approach that matches the measured pace of stellar and planetary evolution. The statistical frameworks astronomers use to estimate galactic planet populations rely on careful extrapolation from observed samples to broader populations, accounting for observational biases and detection limitations. This process requires sophisticated mathematical modeling that combines observational data with theoretical understanding of planet formation and evolution. Bayesian statistical methods play an increasingly important role in these analyses, allowing researchers to combine multiple sources of information while properly accounting for uncertainties and prior knowledge. These techniques help transform incomplete observational data into meaningful constraints on planetary abundance and characteristics across the galaxy. The Drake equation continues to provide a useful framework for organizing our thinking about the factors that influence the abundance of life in the universe, even though many of its terms remain highly uncertain. Recent exoplanet discoveries have begun to constrain the astronomical terms in the equation with observational data rather than pure speculation, though the biological terms remain largely unknown. Current estimates suggest that the number of stars in our galaxy, the fraction of stars with planetary systems, and the number of planets per system are all larger than early versions of the Drake equation assumed. However, the additional requirements for maintaining stable habitable conditions over billions of years may impose constraints that reduce the effective number of life-bearing worlds below optimistic early estimates. The temporal evolution of habitability adds another dimension to these considerations. As stellar brightness changes, atmospheric evolution and geological activity all influence whether planets can maintain life-friendly conditions throughout their histories. A comprehensive assessment of galactic habitability requires understanding not just current conditions, but the entire evolutionary trajectories of planetary systems over cosmic time. Climate modeling studies suggest that planets with active carbon cycles and plate tectonics might be able to regulate their surface temperatures over long periods, maintaining habitability even as their host stars evolve and brighten. However, these self-regulating climate systems require specific combinations of planetary mass, atmospheric composition, and geological activity that may be less common than simple orbital considerations would suggest. The role of large moons in stabilizing planetary climates represents another factor that could influence the abundance of long-term habitable worlds. Our own moon helps stabilize Earth's axial tilt, preventing dramatic climate variations that might otherwise occur as gravitational perturbations from other planets slowly alter our orbital orientation. Planets lacking large stabilizing moons might experience more chaotic climate evolution that reduces their habitability over geological time. The detection of exomoons remains beyond current observational capabilities, though future space missions may be able to identify the largest moon systems around nearby exoplanets. These observations could reveal whether moon systems like our own Earth-Moon pair are common, and whether they contribute significantly to planetary habitability. Jupiter's gravitational influence on our solar system provides another example of how system-wide effects can influence habitability. Jupiter likely protects Earth from frequent large impacts, while also helping to deliver water and organic compounds during the early stages of planetary formation. However, Jupiter's presence may have also prevented the formation of additional rocky planets in what is now the asteroid belt. The diversity of planetary system architectures revealed by exoplanet surveys suggests that Jupiter-like protection may be less common than once assumed. Many observed planetary systems lack massive outer planets that could provide similar protective effects, though alternative configurations might offer different advantages for maintaining habitable conditions. The study of asteroid and comet populations in exoplanetary systems remains largely beyond current observational capabilities. Though future instruments may be able to detect dust and debris that indicate active impact processes, understanding impact rates on exoplanets would provide crucial information for assessing their habitability, as moderate impact rates might benefit life by delivering essential materials, while excessive bombardment could prove destructive. The chemical composition of exoplanets provides another layer of complexity in assessing their potential habitability. Planets forming in different regions of the galaxy or around stars with different metallicities may have access to different inventories of elements essential for life as we know it. Carbon, nitrogen, phosphorus, and other biological elements must be present in appropriate abundances and chemical forms to support the complex chemistry of living systems. Recent spectroscopic observations of exoplanet atmospheres have begun to reveal the chemical diversity of these distant worlds, with some showing evidence for unusual compositions that challenge our understanding of planetary formation and evolution. These discoveries highlight the importance of chemical factors in determining habitability beyond simple physical parameters like size and orbital distance. The abundance of water in exoplanetary systems represents a crucial factor for habitability that remains difficult to assess with current observational techniques. While water appears to be common throughout the universe, its distribution and availability on planetary surfaces depend on complex interactions between atmospheric chemistry, geological processes, and stellar radiation that vary significantly between different types of planetary systems. Computer models of planetary water cycles suggest that maintaining surface oceans requires delicate balances between water delivery, atmospheric retention, and geological recycling that may be sensitive to small changes in planetary or stellar properties. Understanding these water cycle dynamics helps astronomers assess which types of exoplanets are most likely to maintain the liquid water essential for life as we know it. The search for water vapor in exoplanet atmospheres has become one of the primary goals of current atmospheric characterization efforts, as its presence would indicate not only atmospheric retention, but also potential surface reserves. However, distinguishing between water vapor from surface evaporation and that produced by atmospheric chemistry or comet impacts requires careful analysis of atmospheric composition and dynamics. Recent detections of water vapor in several exoplanet atmospheres have provided valuable insights into atmospheric chemistry and dynamics, though most of these observations involve hot, gas giant planets rather than potentially habitable terrestrial worlds. Extending these techniques to smaller, cooler planets remains a significant observational challenge that will require more sensitive instruments and longer observation times. The James Webb Space Telescope represents a major advance in our ability to detect and characterize water vapor and other atmospheric constituents in exoplanet atmospheres. Its infrared sensitivity allows it to observe molecular absorption features that are inaccessible to visible light telescopes, opening new windows into exoplanet atmospheric chemistry. Early results from Webb's exoplanet observations have already revealed unexpected atmospheric complexity, with some worlds showing evidence for clouds, hazes, and chemical compositions that differ significantly from theoretical predictions. These discoveries underscore the diversity of possible atmospheric environments and the importance of observational data in constraining theoretical models. The statistical picture of exoplanet atmospheric diversity continues to evolve as larger samples of characterized atmospheres become available. Current observations suggest that atmospheric composition varies widely, even among planets with similar sizes and orbital properties, indicating that formation and evolutionary history play crucial roles in determining final atmospheric states. Understanding this atmospheric diversity helps astronomers refine estimates of how many potentially habitable worlds might actually maintain suitable surface conditions over long periods. Planets that appear promising based on their orbital properties might prove uninhabitable if their atmospheric evolution follows paths similar to Venus, while others might maintain habitability through mechanisms that aren't captured in simple models. The role of stellar activity in atmospheric evolution continues to be refined through both observational studies and theoretical modeling. Recent observations of stellar flares and their impact on planetary atmospheres have revealed complex interactions that depend on planetary magnetic field strength, atmospheric composition, and the specific characteristics of stellar radiation. Some studies suggest that moderate levels of stellar activity might actually benefit habitability by driving atmospheric chemistry that produces essential prebiotic compounds, while excessive activity clearly poses threats to atmospheric retention and surface habitability. Finding the optimal balance between beneficial and harmful stellar influences represents an active area of current research. The magnetic field protection hypothesis suggests that planets with strong magnetic fields might be able to maintain their atmospheres even around active stars, while those lacking magnetic protection would lose their atmospheres more rapidly. However, generating strong magnetic fields requires planetary properties, including size, composition, and thermal evolution, that may be less common than simple size distributions would suggest. Recent studies of magnetic field generation in exoplanets remain largely theoretical due to the difficulty of directly measuring exoplanetary magnetic properties with current instruments. Future missions may be able to detect the radio emissions or other signatures of exoplanetary magnetic fields, providing crucial data for understanding atmospheric retention around different types of stars. The thermal evolution of planetary interiors influences magnetic field generation, geological activity, and atmospheric chemistry over billions of years. Planets that cool too quickly may lose their magnetic fields and geological activity, reducing their ability to maintain habitable surface conditions. Those that remain too hot may experience excessive volcanic activity that creates uninhabitable atmospheric compositions. Finding the optimal thermal evolution pathway for long-term habitability requires understanding the complex interactions between planetary size, composition, orbital properties, and tidal heating that determine internal heat budgets over cosmic time. This represents another dimension of planetary habitability that extends well beyond simple orbital considerations. As you rest comfortably and let these intricate connections flow through your awareness, consider how each factor we've explored represents just one piece of a vast puzzle that determines whether distant worlds can maintain the conditions necessary for life. The complexity of these interactions helps explain why estimating the abundance of truly habitable worlds remains such a challenging scientific endeavor. The beauty of this complexity lies not in its difficulty, but in the elegant ways that physical laws govern planetary evolution across the universe. The same gravitational, thermal, and chemical processes that shaped Earth's history operate on countless worlds throughout the galaxy, creating environments that may be remarkably diverse, yet governed by the same fundamental principles we can study and understand. Current technological capabilities represent just the beginning of our ability to characterize these distant environments in detail. The next generation of space telescopes and ground-based instruments will dramatically expand our ability to study exoplanet atmospheres, surface properties, and system architectures with unprecedented precision and sensitivity. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter, providing light-gathering power and resolution that will enable direct imaging and spectroscopy of nearby exoplanets. Combined with advanced adaptive optic systems, this instrument will be capable of studying atmospheric chemistry and even detecting seasonal variations on the most favorable targets. Space-based mission concepts, including starshades and advanced coronagraphs, promise to complement ground-based capabilities by providing the ultra-stable observing conditions needed for direct imaging of Earth-like planets around Sun-like stars. These missions would represent the culmination of decades of technological development aimed at answering fundamental questions about planetary habitability and the prevalence of life in the universe. The scientific return from these future observations will depend not just on instrumental capabilities, but also on the theoretical frameworks we develop for interpreting complex atmospheric and surface data. Understanding how to distinguish between biological and non-biological sources of atmospheric gases, how to assess surface habitability from orbital observations, and how to account for evolutionary effects in interpreting current conditions all require continued development of our theoretical understanding. International collaboration will play an increasingly important role as these observational capabilities come online, with research teams around the world working together to plan observations, share data, and develop theoretical interpretations. The questions we're addressing transcend national boundaries and represent shared human interests in understanding our cosmic environment. The patient accumulation of observational data over the coming decades will gradually transform our understanding from statistical estimates based on limited samples toward detailed knowledge of individual planetary systems and their characteristics. This transition from statistical to detailed understanding represents a fundamental shift in how we approach questions about planetary habitability and the abundance of life-bearing worlds. Each newly characterized exoplanet atmosphere, each confirmed rocky planet in a habitable zone, each atmospheric biosignature detection or non-detection will add to our understanding, while often raising new questions that require additional observations and theoretical development. This iterative process of discovery reflects the natural progression of scientific understanding in complex fields. The societal implications of discovering life on other worlds have been the subject of extensive discussion among scientists, ethicists, and policymakers. However, the actual discovery process will likely unfold gradually through the accumulation of evidence rather than through a single dramatic revelation, allowing time for thoughtful consideration of the implications and appropriate responses. The search for life elsewhere also influences our perspective on Earth's biosphere and our responsibilities as planetary stewards. Whether life proves common or rare, the detailed study of exoplanets enhances our appreciation for the remarkable complexity and apparent fragility of the conditions that have allowed life to flourish on our own world for billions of years. Climate change research benefits significantly from exoplanet studies, as understanding how planetary atmospheres evolve under different conditions provides crucial insights into the factors that control long-term climate stability. The atmospheric evolution of Venus and the climate history of Mars offer sobering examples of how planetary climates can evolve away from habitable conditions. Conversely, studying Earth's climate system in the context of exoplanetary diversity helps us appreciate the remarkable resilience that has maintained stable conditions conducive to life for nearly 4 billion years. The delicate balance of factors that have preserved our planet's habitability provides a template for understanding what we might seek in distant worlds, while also highlighting the extraordinary nature of our cosmic home. The carbon cycle on Earth demonstrates the kind of planetary self-regulation that might be necessary for long-term habitability. Over geological timescales, volcanic activity releases carbon dioxide into the atmosphere, while weathering of rocks slowly removes it, creating a natural thermostat that has helped maintain temperate surface conditions even as solar brightness has increased by 30% since life first emerged. This carbonate-silicate cycle requires active geology, liquid water, and continental landmasses to operate effectively. Planets lacking these features might experience runaway climate change in either direction, becoming too hot or too cold to maintain surface habitability despite initially favorable conditions. Understanding these feedback mechanisms helps astronomers assess which types of exoplanets might maintain stable climates over the billions of years required for life to evolve complexity. The presence of plate tectonics on Earth plays a crucial role in maintaining habitability by recycling carbon between the atmosphere and planetary interior. Without this geological activity, carbon dioxide would gradually accumulate in the atmosphere through volcanic outgassing, potentially creating a runaway greenhouse effect similar to what occurred on Venus. Alternatively, if weathering processes dominated without volcanic replenishment, atmospheric carbon dioxide might be depleted to levels that would freeze the planet. Whether plate tectonics operates on other worlds depends on planetary size, internal heat production, and the presence of water to lubricate geological processes. Computer models suggest that planets significantly smaller than Earth might cool too quickly to maintain active geology, while much larger worlds might have such thick crusts that plate tectonics cannot operate. This creates another constraint on the types of exoplanets that might sustain long-term habitability. The role of water in planetary geology extends beyond surface oceans to include its influence on mantle convection, volcanic activity, and the formation of continental crust. Water acts as a lubricant that enables plate tectonics, while also influencing the chemistry of volcanic gases and the weathering rates of surface rocks. These interconnected processes create complex feedback loops that help regulate planetary climate over geological time. Recent studies of exoplanet interior structure have begun to constrain the range of compositions and thermal properties that characterize rocky worlds around other stars. Some exoplanets appear to have much higher iron content than Earth, which could affect their magnetic field generation and geological evolution. Others may be dominated by lighter elements that would create very different internal dynamics and surface conditions. The diversity of stellar metallicities throughout our galaxy adds another layer of complexity to understanding exoplanet compositions and habitability. Stars that formed from gas clouds with lower abundances of heavy elements would produce planets with different chemical inventories that might lack some elements essential for Earth-like life or geological processes. Conversely, stars with very high metallicities might produce planets rich in radioactive elements that could maintain internal heat for much longer periods, potentially extending the duration of geological activity and magnetic field generation. However, excessive radioactivity could also create surface radiation levels that would be harmful to most forms of life. The temporal evolution of stellar metallicity in our galaxy means that the abundance and characteristics of potentially habitable planets have likely changed significantly over cosmic history. Early generations of stars had lower metallicities that might have produced fewer rocky planets or planets, with compositions less suitable for maintaining Earth-like conditions. As you breathe deeply and let these cosmic timeframes drift through your consciousness, consider how our galaxy has been slowly enriching itself with heavy elements for over 13 billion years. Each generation of stars has contributed to this chemical evolution by fusing lighter elements into heavier ones and dispersing these products through supernova explosions and stellar winds. This gradual chemical enrichment means that potentially habitable planets forming today might have access to different elemental abundances than those that formed billions of years ago. Whether this temporal evolution favors or hinders the development of life remains an open question that depends on the specific requirements for planetary habitability and biological chemistry. The search for atmospheric biosignatures on exoplanets represents our most promising near-term approach to detecting life beyond Earth. However, interpreting these chemical signals requires understanding not just what gases life might produce, but also how geological processes, atmospheric chemistry, and stellar radiation could create similar signatures without biological involvement. Oxygen remains the most promising biosignature gas because it reacts so readily with other atmospheric constituents that it requires continuous replenishment to maintain significant concentrations. On Earth, photosynthesis by plants and microorganisms produces essentially all atmospheric oxygen, making it a strong indicator of biological activity when found in combination with water vapor and other gases. However, photochemical processes driven by stellar ultraviolet radiation can also split water molecules and release oxygen, creating potential false positive biosignatures. Distinguishing between biological and abiotic sources of atmospheric oxygen requires careful analysis of oxygen concentrations, accompanying gases, and stellar radiation levels. Methane presents another potential biosignature, as it has a short atmospheric lifetime and requires ongoing production to maintain detectable levels. On Earth, most methane comes from biological sources including microorganisms, though geological processes can also produce significant quantities through reactions between water and certain types of rocks. The simultaneous presence of oxygen and methane in an exoplanet's atmosphere would be particularly intriguing, because these gases normally react with each other quickly. Maintaining both gases simultaneously would require ongoing production of each, suggesting either very active geology or biological processes that produce one or both components. Future atmospheric characterization studies will focus on detecting combinations of gases that would be difficult to explain through purely geological processes. Water vapor, oxygen, and ozone together would create a compelling case for photosynthetic life, while unusual ratios of different gases might indicate biological metabolism or other life processes. The James Webb Space Telescope has already demonstrated the precision required for these atmospheric studies by detecting water vapor, carbon dioxide, and other molecules in several exoplanet atmospheres. However, most of these early observations have focused on large, hot planets that are easier to study, but less likely to harbour life as we understand it. Extending these atmospheric characterization techniques to smaller, cooler planets that might actually be habitable represents one of the greatest challenges in current exoplanet science. The atmospheric signals from Earth-sized planets are much weaker than those from gas giants, requiring longer observation times and more sensitive instruments to achieve useful precision. The statistical approach to understanding biosignature detection emphasizes the importance of studying large samples of planetary atmospheres to distinguish genuine biosignatures from false positives. Individual detections of potentially biological gases might be ambiguous, but patterns across many worlds could reveal the signatures that genuinely indicate life. Current estimates suggest that definitively detecting biosignatures on potentially habitable exoplanets will require observing dozens or hundreds of candidate worlds to build sufficient statistical confidence. This observational program will likely span decades and require multiple generations of increasingly sensitive telescopes and analytical techniques. The collaborative nature of this endeavour reflects the global human interest in answering fundamental questions about life in the universe. Research teams around the world are working together to develop observational strategies, share data, and create theoretical frameworks for interpreting complex atmospheric measurements. As these observational capabilities develop over the coming decades, we may gradually transition from asking whether life exists elsewhere to understanding how common it might be and what forms it takes under different planetary conditions. This progression from detection to characterization represents a natural evolution in our approach to studying life beyond Earth. The philosophical implications of these potential discoveries have been contemplated by scientists, philosophers, and ethicists for decades, though the actual process of discovery will likely unfold gradually through accumulating evidence rather than dramatic revelations. This measured pace allows time for thoughtful consideration of the implications and appropriate responses to what we might learn. Whether we ultimately discover that life is common or rare throughout the galaxy, The search itself has already transformed our understanding of planetary systems and our place within the cosmic environment. Each exoplanet discovery, each atmospheric characterization, each refinement of habitability models adds to humanity's growing appreciation for the complexity and beauty of the universe. The current phase of exoplanet science represents just the beginning of what promises to be centuries of exploration and discovery. As our observational capabilities continue to improve and our theoretical understanding deepens, future generations will have access to detailed knowledge about thousands of potentially habitable worlds and their characteristics. The patient accumulation of this knowledge reflects the inherently gradual nature of scientific progress in addressing such fundamental questions. Unlike the dramatic discoveries often portrayed in science fiction, real progress in understanding exoplanet habitability proceeds through careful observation, mathematical analysis, and gradual refinement of theoretical models. This methodical approach ensures that our conclusions rest on solid observational foundations rather than speculation or wishful thinking. When we speak of potentially habitable exoplanets, we're discussing worlds with measured properties that place meaningful constraints on their possible characteristics and environmental conditions. The uncertainty ranges in current estimates of galactic habitability reflect the honest limitations of human knowledge rather than any failure of scientific methodology. We observe only a tiny fraction of our galaxy's stellar population, detect only the most easily observable planetary systems, and can characterize atmospheres only for the most favorable targets. Acknowledging these limitations allows us to express our current understanding appropriately, while recognizing that future observations will undoubtedly refine and possibly revolutionize our perspective on planetary habitability and the abundance of life-bearing worlds. The exponential growth in exoplanet discoveries over the past 3 decades suggests that the rate of progress will continue accelerating as new missions launch and observational techniques improve. Each technological advance expands our ability to detect smaller planets, characterize fainter atmospheric signals, and study more distant and diverse planetary systems. Future ground-based telescopes with primary mirrors 30 to 40 meters in diameter will provide unprecedented light-gathering power and resolution for studying nearby exoplanets. These instruments will enable direct imaging and detailed spectroscopic analysis of potentially habitable worlds around the nearest Sun-like stars. Space-based missions specifically designed for exoplanet characterization will complement ground-based observations by providing the ultra-stable conditions needed for precision measurements. Advanced coronagraph technologies will enable direct imaging of Earth-like planets by blocking out the overwhelming brightness of their host stars. The technical challenges involved in these observations continue to drive innovations in precision optics, spacecraft engineering, and data analysis techniques. Success in directly imaging and characterizing Earth-like exoplanets will represent one of humanity's greatest technological achievements, comparable to landing on the moon or detecting gravitational waves. As you rest peacefully and let your mind drift among these future possibilities, consider how each advance in our observational capabilities brings us closer to answering questions that have fascinated humanity for millennia. The patient development of these precision instruments reflects our deep curiosity about whether Earth-like conditions exist elsewhere in the universe. The collaborative international effort required for these ambitious projects demonstrates how the search for life beyond Earth brings out the best aspects of human cooperation and shared purpose. Scientists and engineers from around the world work together on these challenging endeavors, united by common curiosity about our cosmic environment. The gradual nature of scientific progress in this field creates opportunities for thoughtful consideration of the implications as our understanding evolves. Rather than sudden revelations that might be difficult to process, the steady accumulation of knowledge allows society to gradually adapt its perspective on humanity's place in the universe. Educational institutions play a crucial role in preparing future generations of scientists and engineers who will continue this exploration. The current generation of students will likely witness the first definitive detections of life beyond Earth and will be responsible for developing even more sophisticated techniques for studying distant worlds. Public engagement with exoplanet science has grown dramatically as discoveries capture imaginations around the world. The inherently universal nature of these questions transcends cultural and national boundaries, creating shared human interest in what we might discover among the stars. The economic implications of exoplanet research extend beyond pure scientific curiosity to include technological innovations that benefit numerous other fields. Precision instrumentation, developed for exoplanet observations, often finds applications in medical imaging, telecommunications, and other technologies that improve human life. The philosophical and spiritual dimensions of potentially discovering life elsewhere have been explored by thinkers from many different traditions and perspectives. Whether such discoveries would fundamentally challenge existing worldviews or simply expand them remains a subject of ongoing discussion and contemplation. Current estimates of potentially habitable exoplanets provide a framework for thinking about these questions, while acknowledging the substantial uncertainties involved. The ranges we've explored tonight, from hundreds of millions to tens of billions of potentially life-bearing worlds in our galaxy alone, span enormous numerical territory that reflects our current limitations in understanding planetary habitability. These vast numbers, whether at the conservative or optimistic end of current estimates, suggest that Earth-like conditions may not be unique in the universe. However, the specific combination of factors that has allowed life not just to emerge but to persist and evolve complexity over billions of years may be considerably rarer than simple orbital considerations would suggest. The temporal dimension of habitability adds another layer of consideration to these estimates. Planets must not only achieve habitable conditions, but maintain them over the enormous timescales required for life to evolve from simple chemistry to the complex organisms we observe on Earth. This requirement for long-term stability may significantly reduce the effective number of life-bearing worlds at any given time. Conversely, the extreme longevity of many stellar types, particularly red dwarf stars, means that potentially habitable worlds could maintain suitable conditions for hundreds of billions of years, far longer than the current age of the universe. This extended temporal perspective suggests that the total number of life-bearing worlds that have existed or will exist over cosmic history could be vastly larger than the number that exist at any single moment. The question of temporal overlap becomes relevant when considering whether life might develop on different worlds simultaneously, or whether biological activity might be separated by vast gulfs of time and space. Even if life is common over cosmic history, the specific timing of its emergence and evolution might mean that most life-bearing worlds exist in isolation from one another. These temporal considerations remind us that when we ask how many Earths could exist right now, we're really asking about a snapshot of a much larger cosmic story that unfolds over billions of years. The current moment represents just one frame in an enormously long film that includes the entire history and future evolution of life in the universe. Our own existence at this particular time in cosmic history, when exoplanet science is just becoming possible and we're beginning to answer these ancient questions, represents a remarkable convergence of technological capability and cosmic timing. We live at perhaps the first moment in the universe's history when intelligent life could begin to assess the abundance of habitable worlds and the prevalence of life itself. This perspective suggests that our current efforts to understand exoplanet habitability may represent not just scientific curiosity, but a crucial step in the universe's own process of self-awareness. Through human consciousness and scientific investigation, the cosmos begins to understand itself and its potential for harboring life and intelligence. The gentle rhythm of discovery in this field reflects the patient nature of cosmic processes themselves. Stars form slowly from collapsing gas clouds, planets accrete gradually from swirling debris disks, and life evolves over geological timescales that dwarf human civilization. Our scientific understanding develops through similarly patient accumulation of observations and insights. This measured pace of progress allows for deep appreciation of each discovery and careful consideration of its implications. Rather than rushing toward quick answers, the scientific community has developed a culture of thorough peer review and replication that ensures our conclusions rest on solid foundations. The international cooperation required for modern exoplanet research creates a model for how humanity might approach other challenges that transcend national boundaries. The shared curiosity about life in the universe brings together people from different cultures and backgrounds in pursuit of common understanding. As you breathe slowly and let these thoughts settle gently in your mind, consider how the search for other Earths connects us to the deepest questions about existence itself. Whether we are alone or accompanied by countless other worlds harboring life, the investigation itself represents one of humanity's most profound intellectual achievements. The tools we've developed to peer across interstellar space and analyze the atmospheric chemistry of distant worlds showcase human ingenuity applied to questions of cosmic significance. These instruments represent extensions of human senses that allow us to perceive environments far beyond the reach of direct exploration. The mathematical frameworks we use to understand planetary formation, atmospheric evolution, and stellar life cycles demonstrate how human reason can comprehend processes operating on scales of time and space that exceed direct experience. Through careful observation and logical analysis, we can understand cosmic phenomena, despite their vast scales and immense complexity. The collaborative networks of scientists who share data, develop theories, and peer review each other's work create a collective intelligence that transcends individual limitations. This scientific community represents humanity's organized effort to understand the natural world and our place within it. Current estimates suggest that our galaxy contains somewhere between hundreds of millions and tens of billions of potentially habitable worlds. These numbers, while uncertain, provide a framework for thinking about the cosmic abundance of environments where life might emerge and flourish. Even the most conservative estimates suggest that potentially habitable worlds number in the hundreds of millions throughout our galaxy alone. When we consider that our galaxy is just one among trillions in the observable universe, the total number of potentially life-bearing environments becomes almost incomprehensibly large. Yet the requirements for maintaining long-term habitability appear sufficiently restrictive that Earth-like worlds, while perhaps not unique, may be considerably rarer than optimistic extrapolations would suggest. The delicate balance of factors that has maintained our planet's habitability for billions of years may represent a relatively uncommon outcome of planetary evolution. The ongoing characterization of exoplanet atmospheres will help resolve these questions by revealing which potentially habitable worlds have actually maintained the conditions necessary for surface water and stable climates. These observations will also help us understand the range of atmospheric compositions that might support life, potentially expanding our definition of habitability beyond strictly Earth-like parameters. The search for biosignatures in exoplanet atmospheres represents our most promising near-term approach to detecting life beyond Earth, though interpreting these chemical signals will require careful analysis to distinguish biological from geological sources. The accumulation of atmospheric data from many worlds will gradually build our understanding of the factors that control planetary habitability. Future space missions specifically designed for exoplanet characterization will dramatically expand our capabilities for studying potentially habitable worlds. These instruments will enable direct imaging and detailed atmospheric analysis of Earth-like planets around nearby Sun-like stars, providing unprecedented insights into planetary diversity and habitability. The patient development of these observational capabilities reflects the long-term nature of progress in addressing fundamental questions about life in the universe. Unlike questions that can be answered through single experiments or observations, understanding the cosmic abundance of life requires accumulating evidence from many different sources over extended periods. This gradual approach to discovery allows for thoughtful consideration of the implications as our understanding evolves. Rather than sudden revelations that might be difficult to process, the steady progression of knowledge provides opportunities for society to adapt its perspective on humanity's cosmic significance. The educational value of exoplanet research extends far beyond professional astronomy to inspire students and the general public with questions about the nature of life and our place in the universe. These investigations demonstrate how scientific methods can address profound philosophical questions through careful observation and logical analysis. The technological innovations driven by exoplanet research benefit numerous other fields through the development of precision instruments, data analysis techniques, and engineering solutions for challenging observational problems. The pursuit of knowledge about distant worlds creates practical benefits that improve human capabilities in many different areas. As you continue to rest comfortably and breathe slowly, let your mind embrace the magnificent uncertainty of these cosmic questions. We stand at the threshold of potentially discovering that life is abundant throughout the universe, or alternatively, that Earth represents a rare and precious example of what cosmic evolution can achieve under favorable circumstances. Either outcome would profoundly influence our understanding of biology, our responsibilities as planetary stewards, and our perspective on humanity's role in the cosmic story. The search itself, regardless of what we ultimately discover, represents one of our species' most noble endeavors, extending human consciousness across vast distances to explore fundamental questions about existence. The gentle precision required for these investigations showcases the remarkable capabilities that emerge when human curiosity combines with patient methodology and technological innovation. Each photon of starlight that reveals information about a distant world represents a connection across space and time that links us to cosmic environments we may never visit directly. The collaborative nature of modern astronomy creates a global community, united by shared wonder about the universe and its contents. Scientists from different countries, cultures, and backgrounds work together on these investigations, demonstrating how the pursuit of knowledge can transcend earthly divisions and create bonds based on common curiosity. The questions we're addressing through exoplanet research connect us to the deepest human impulses toward exploration and understanding. Since ancient times, people have looked at the night sky and wondered whether other worlds might exist among the stars. Only recently have we developed the technological capability to transform these age-old questions into observational science. The gradual transition from speculation to measurement represents a fundamental shift in how we approach questions about life in the universe. Where previous generations could only imagine what other worlds might be like, we can now detect their presence, measure their properties, and begin to assess their potential for harboring life. This transformation from imagination to observation demonstrates the power of scientific methodology to address questions that once seemed forever beyond human knowledge. The careful application of physics, chemistry, and mathematics allows us to study environments separated from us by vast distances and unimaginable timescales. The results of these investigations, whether they reveal life to be common or rare, will influence human perspectives on existence for generations to come. We live at a unique moment in cosmic history when these ancient questions are finally becoming answerable through direct observation rather than speculation. Current evidence suggests that rocky planets are common throughout our galaxy, with many orbiting within their stars' habitable zones where liquid water could potentially exist on their surfaces. However, the additional requirements for maintaining stable, temperate climates over billions of years may impose significant constraints that render truly Earth-like worlds considerably rarer. The statistical estimates we've explored tonight, ranging from hundreds of millions to tens of billions of potentially habitable worlds in our galaxy, reflect both the promise and the uncertainty inherent in current observations. These ranges will narrow as our observational databases grow larger and our theoretical understanding deepens. The exponential growth in exoplanet discoveries over recent decades suggests that the pace of progress will continue accelerating as new instruments come online and observational techniques improve, future generations will likely have access to detailed information about thousands of potentially habitable worlds and their atmospheric characteristics. Whether life proves common or rare among these worlds, the search itself has already transformed our understanding of planetary systems and our appreciation for the complexity of factors that influence habitability. Each discovery adds to humanity's growing knowledge of the cosmic environment that gave rise to our own remarkable planet. The philosophical implications of these investigations extend beyond scientific curiosity to influence how we view our responsibilities as inhabitants of what may be a rare and precious world. Whether Earth is unique or one among many life-bearing planets, understanding its cosmic context enhances our appreciation for the conditions that have allowed life to flourish here. The gentle rhythm of scientific discovery in this field mirrors the cosmic processes we study, with understanding accumulating gradually through patient observation and careful analysis. This measured approach ensures that our conclusions rest on solid foundations, while allowing time for thoughtful consideration of the implications. As you breathe deeply and let these vast perspectives settle peacefully in your consciousness, consider how the search for other Earths represents humanity at its best, applying intelligence, creativity, and international cooperation to address questions of profound significance. Regardless of what we ultimately discover about life elsewhere, the investigation itself stands as a testament to human curiosity and our deep desire to understand our place in the magnificent cosmos. The numbers we've explored tonight, from thousands of confirmed exoplanets to billions of potential Earth-like worlds, provide a framework for thinking about cosmic abundance, while acknowledging the substantial uncertainties that remain. These estimates will undoubtedly be refined as our knowledge expands, but they offer a glimpse into the remarkable richness of planetary environments throughout our galaxy. Whether you find comfort in the possibility that Earth is unique and precious, or excitement in the prospect that life may be abundant among the stars, these questions connect us to the deepest mysteries of existence. The patient pursuit of answers through scientific observation represents one of humanity's most profound adventures, extending our awareness across cosmic distances to explore the fundamental nature of life itself. Sleep peacefully, knowing that while these questions may take generations to fully answer, each night brings new observations from telescopes around the world and in space, gradually building our understanding of the cosmic environment we call home. The universe may be vast and mysterious, but through careful observation and patient analysis, we slowly illuminate its secrets, one distant world at a time. As you continue to rest peacefully, breathing slowly, and letting your mind drift through these cosmic possibilities, we arrive at perhaps the most challenging aspect of estimating Earth-like worlds. The transition from potentially habitable to actually inhabited represents a leap that science can describe but not yet definitively measure across the vast distances of space. The chemical signatures that might indicate life on distant worlds require extraordinary precision to detect and even greater care to interpret correctly. When we speak of biosignatures, we're discussing molecules in planetary atmospheres that could suggest biological processes, though distinguishing these from purely geological chemistry remains one of the most delicate challenges in modern astronomy. Consider how life on Earth has gradually transformed our planet's atmospheric composition over billions of years. The oxygen we breathe exists in our atmosphere primarily because of photosynthesis, a biological process that has been operating for roughly 3 billion years. Without the continuous activity of plants, algae, and certain bacteria, atmospheric oxygen would react with surface rocks and disappear within a few million years. This reactive nature of oxygen makes it a compelling biosignature when found in substantial concentrations alongside water vapor. However, stellar radiation can also split water molecules and release oxygen through purely chemical processes, creating potential false signals that require careful analysis to understand properly. The James Webb Space Telescope has begun this delicate detective work, analyzing the atmospheric compositions of exoplanets by studying how starlight changes as it passes through their gaseous envelopes. Each molecule absorbs specific wavelengths of light, creating a unique fingerprint that can be read across interstellar distances with sufficient patience and precision. These early atmospheric studies have revealed remarkable diversity among exoplanets, with some worlds showing thick clouds of exotic compounds, while others appear to have lost most of their original atmospheres entirely. The complexity of these atmospheric environments reminds us that each planet represents a unique evolutionary experiment spanning billions of years. The search for water vapor in exoplanet atmospheres has become a priority because liquid water appears essential for life as we understand it. However, detecting water vapor requires distinguishing between molecules produced by surface evaporation, atmospheric chemistry, or delivery by comets and asteroids, each of which tells a different story about planetary conditions. Recent observations have successfully identified water vapor in the atmospheres of several exoplanets, though most of these detections involve large hot worlds, quite unlike Earth. Extending these techniques to smaller, cooler planets that might actually harbour surface oceans represents a significant observational challenge requiring more sensitive instruments and longer observation periods. The statistical approach to understanding atmospheric biosignatures emphasizes studying large samples of planetary atmospheres to identify patterns that might distinguish biological from geological processes. Individual detections of potentially biological gases might remain ambiguous, but systematic studies of many worlds could reveal the chemical signatures that genuinely indicate life. Computer models suggest that confirming atmospheric biosignatures will require observing dozens or hundreds of candidate worlds to build sufficient statistical confidence. This observational program will likely span decades and involve multiple generations of increasingly sophisticated telescopes and analytical techniques. The collaborative nature of this endeavour reflects the global human interest in addressing fundamental questions about life in the universe. Research teams from different countries work together to plan observations, share data, and develop theoretical frameworks for interpreting complex atmospheric measurements. As these observational capabilities develop over the coming years, we may gradually transition from asking whether life exists elsewhere to understanding how common it might be and what forms it takes under different planetary conditions. This evolution from detection to characterization represents a natural progression in our approach to studying life beyond Earth. The philosophical implications of potentially discovering life on other worlds have been contemplated by scientists and thinkers for generations, though the actual process of discovery will likely unfold gradually through accumulating evidence rather than sudden revelations. This measured pace allows time for thoughtful consideration of what such discoveries might mean for our understanding of life and our place in the universe. Whether we ultimately find that life is common or rare among exoplanets, the search itself has already transformed our perspective on planetary systems and the factors that influence habitability. Each atmospheric characterization, each confirmed rocky planet in a habitable zone, adds to humanity's growing appreciation for the complexity and beauty of cosmic environments. The current phase of exoplanet atmospheric studies represents just the beginning of what promises to be centuries of detailed exploration. Future instruments will provide unprecedented sensitivity for detecting trace gases that might indicate geological activity, weather patterns, or even biological processes on distant worlds. The extremely large telescope, currently under construction in Chile, will combine a mirror 39 meters in diameter with advanced adaptive optics to study nearby exoplanets in extraordinary detail. This instrument will be capable of directly imaging some exoplanets and analyzing their atmospheric compositions through spectroscopy, potentially revealing seasonal changes and long-term atmospheric evolution. Space-based telescopes, designed specifically for exoplanet characterization, will complement these ground-based capabilities by providing the ultra-stable observing conditions needed for precision measurements. Advanced coronagraph technologies will enable direct observation of Earth-like planets by suppressing the overwhelming brightness of their host stars. The technical challenges involved in these observations continue to drive innovations in precision optics, spacecraft engineering, and data analysis that push the boundaries of current technological capabilities. Success in these endeavors will represent remarkable achievements in human ingenuity applied to questions of profound cosmic significance. As you breathe slowly and let these technological marvels drift through your consciousness, consider how each advance brings us closer to understanding the true abundance of worlds like our own. The patient development of these instruments reflects humanity's deep curiosity about whether the conditions that gave rise to life on Earth exist elsewhere in the universe. The process of discovery in this field unfolds at a pace that mirrors the cosmic phenomena we study. Planetary formation occurs over millions of years, stellar evolution spans billions of years, and atmospheric evolution operates over timescales that dwarf human civilization. Our scientific understanding develops through similarly patient accumulation of observations and theoretical insights. This measured approach to discovery ensures that our conclusions rest on solid observational foundations rather than speculation or wishful thinking. When we speak of potentially habitable exoplanets, we're discussing worlds with measured properties that place meaningful constraints on their possible characteristics and environmental conditions. The uncertainty inherent in current estimates reflects the honest limitations of human knowledge rather than any failure of scientific methodology. We observe only a tiny fraction of our galaxy's stellar population, detect only the most easily observable planetary systems, and can characterize atmospheres only for the most favorable targets. Acknowledging these limitations allows us to express our current understanding appropriately, while recognizing that future observations will undoubtedly refine and possibly transform our perspective on planetary habitability and the abundance of life-bearing worlds throughout the galaxy. The exponential growth in exoplanet discoveries over recent decades suggests that the pace of progress will continue accelerating as new missions launch and observational techniques improve. Each technological advance expands our ability to detect smaller planets, characterize fainter atmospheric signals, and study more distant and diverse planetary systems. Current statistical analyses of exoplanet populations suggest patterns that help us estimate the abundance of potentially habitable worlds throughout our galaxy. These studies indicate that rocky planets similar in size to Earth are relatively common, with many orbiting within their stars' habitable zones where liquid water could theoretically exist. However, the transition from theoretically habitable to actually inhabited requires additional factors that remain difficult to assess with current observational capabilities. Atmospheric retention, magnetic field protection, geological activity, and climate stability all influence whether planets can maintain conditions suitable for life over the billions of years required for biological evolution. The study of our own solar system provides sobering examples of how planets can lose their habitability over geological time. Mars appears to have once hosted flowing water and thick atmospheres, but gradually lost these conditions as its magnetic field weakened and its atmosphere escaped to space. Venus likely experienced a runaway greenhouse effect that transformed it from potentially habitable to utterly inhospitable. These examples highlight the narrow range of conditions that allow planets to maintain temperate climates over cosmic timescales. Earth's successful navigation of this middle path required a fortunate combination of size, composition, orbital properties, and evolutionary history that may be less common than simple habitable zone calculations would suggest. Understanding the factors that control long-term planetary habitability requires studying not just current conditions, but entire evolutionary pathways spanning billions of years. Computer models attempt to simulate these complex processes, revealing the delicate balances that determine whether worlds can sustain life-friendly environments throughout their histories. The role of stellar evolution in planetary habitability adds another temporal dimension to these considerations. Stars gradually brighten as they age, causing habitable zones to migrate outward over billions of years. Planets must either migrate with their star's habitable zone or develop climate regulation mechanisms that can compensate for changing stellar energy input. The concept of a continuously habitable zone attempts to account for stellar evolution by identifying orbital regions where planets could maintain liquid water throughout their star's main sequence lifetime. This more restrictive definition typically yields smaller estimates of long-term habitable real estate than simple snapshot assessments of current conditions. Climate modeling studies suggest that planets with active carbon cycles might regulate their surface temperatures over long periods by adjusting atmospheric greenhouse gas concentrations in response to changing stellar brightness. However, this planetary thermostat requires geological activity, surface water, and continental landmasses to operate effectively. The presence of large moons like Earth's appears to play an important role in maintaining climate stability by preventing dramatic variations in planetary tilt that could otherwise drive extreme climate changes. Whether such stabilizing moon systems are common around exoplanets remains unknown due to the difficulty of detecting exomoons with current instruments. Jupiter's gravitational influence on our solar system demonstrates how giant planets can both protect and threaten inner worlds through their effects on comet and asteroid orbits. Understanding the architecture of exoplanetary systems helps assess whether Earth-like worlds enjoy similar protection from catastrophic impacts. The chemical composition of planetary building materials varies throughout our galaxy, depending on stellar metallicity and the local abundance of heavy elements. Planets forming in different galactic environments may have access to different inventories of elements, essential for geology, atmosphere formation, and potentially biology. Recent spectroscopic studies of exoplanet atmospheres have begun to reveal this chemical diversity, with some worlds showing compositions quite different from what theoretical models predicted. These observations highlight the importance of chemical factors in determining planetary characteristics beyond simple physical parameters like size and orbital distance. The abundance of water in exoplanetary systems represents another crucial factor for habitability that varies significantly between different stellar environments. While water appears common throughout the universe, its delivery to planetary surfaces and retention over geological time depends on complex interactions between atmospheric evolution, impact history, and geological processes. Understanding planetary water cycles requires knowledge of atmospheric dynamics, surface geology, and stellar radiation that operates over timescales much longer than human observation periods. Computer models attempt to simulate these processes, though significant uncertainties remain about how water behaves under the diverse conditions found in exoplanetary systems. The magnetic field protection hypothesis suggests that planets require strong magnetic fields to shield their atmospheres from stellar radiation and maintain habitable surface conditions over long periods. However, generating persistent magnetic fields requires specific combinations of planetary size, composition, and thermal evolution that may be relatively uncommon. Recent theoretical studies of magnetic field generation in exoplanets remain largely unconstrained by observational data due to the difficulty of detecting exoplanetary magnetic properties with current instruments. Future missions may develop techniques for measuring these magnetic environments, providing crucial data for understanding atmospheric retention around different types of stars. The thermal evolution of planetary interiors influences magnetic field generation, geological activity, and atmospheric outgassing over billions of years. Planets that cool too quickly may lose their geological activity and magnetic protection, while those that remain too hot may experience excessive volcanism that creates uninhabitable atmospheric compositions. Finding the optimal thermal evolution pathway for maintaining long-term habitability represents another constraint on the types of exoplanets that might sustain life over cosmic timescales. This thermal balance depends on planetary mass, composition, radioactive element abundance, and tidal heating that varies significantly between different planetary systems. As you continue to rest peacefully, letting these intricate connections flow gently through your awareness, consider how each factor represents just one piece of an enormously complex puzzle that determines whether distant worlds can maintain conditions suitable for life. The beauty of this complexity lies not in its difficulty, but in the elegant ways that physical laws govern planetary evolution throughout the universe. The same gravitational, thermal, and chemical processes that shaped Earth's 4 billion-year history operate on countless worlds across our galaxy, creating environments that may be remarkably diverse, yet governed by fundamental principles we can study and gradually understand through patient observation and theoretical analysis. Current estimates of potentially habitable exoplanets incorporate these various factors to different degrees, creating ranges that span from relatively pessimistic to cautiously optimistic assessments of galactic habitability. Conservative estimates focusing on Earth-like planets around Sun-like stars suggest perhaps hundreds of millions of potentially habitable worlds in our galaxy. More inclusive definitions that consider super-Earth planets, red dwarf systems, and alternative habitability mechanisms yield estimates ranging into the billions of potentially life-bearing environments. However, the fraction of these worlds that actually develop and maintain life remains highly uncertain, given our limited understanding of biological processes and their cosmic requirements. The temporal dimension of these estimates adds further complexity, as the galaxy's population of habitable worlds has likely changed significantly over cosmic history. Early generations of stars had lower abundances of heavy elements that may have produced fewer rocky planets or worlds with compositions less suitable for maintaining Earth-like conditions. Conversely, the gradual chemical enrichment of our galaxy over billions of years means that potentially habitable planets forming today may have access to more diverse elemental inventories than those that formed in the distant past. Whether this chemical evolution favors or hinders the development of life depends on the specific requirements for planetary habitability and biological chemistry. The search for patterns in exoplanet populations continues as observational databases grow larger and more statistically robust. Each newly discovered planetary system adds to our understanding of how planets form and evolve, while often revealing unexpected diversity that challenges theoretical predictions. The remarkable variety of confirmed exoplanets includes worlds with properties unlike anything in our solar system, from super-Earths with thick atmospheres to planets orbiting binary star systems where double sunsets would illuminate alien skies. This diversity suggests that Earth-like conditions may represent just one point on a broad spectrum of potentially habitable environments. Understanding the full range of possible habitability requires studying not just individual planets, but entire planetary system architectures and their evolutionary histories. The gravitational interactions between planets, the influence of stellar companions, and the long-term stability of orbital configurations all affect whether worlds can maintain suitable conditions for life. The ongoing characterization of exoplanet atmospheres provides our most direct window into the environmental conditions on distant worlds. Each successful atmospheric analysis reveals details about temperature, pressure, chemical composition, and potentially weather patterns that help assess habitability and guide future observations. The James Webb Space Telescope has already demonstrated unprecedented precision in these atmospheric studies, detecting molecules like water vapor, carbon dioxide, and methane in exoplanet atmospheres with sensitivity that would have seemed impossible just a decade ago. Future instruments promise even greater capabilities for studying smaller, cooler planets that might actually harbor life. The statistical approach to atmospheric characterization emphasizes studying large samples of planets to understand the range of possible atmospheric compositions and identify those that might indicate biological activity. This systematic approach helps distinguish genuine patterns from observational noise and builds confidence in our interpretations. International collaboration plays an essential role in these investigations, with research teams around the world sharing observational data, theoretical models, and analytical techniques. The questions we're addressing transcend national boundaries and represent shared human interest in understanding our cosmic environment and our place within it. As you rest here now, breathing slowly and letting these vast cosmic perspectives settle gently in your mind, we find ourselves at the quiet edge of one of humanity's greatest questions. The numbers we've explored together tonight span ranges that reflect both the promise and the honest uncertainty of our current understanding. From the thousands of confirmed worlds we can measure directly, to the hundreds of millions or perhaps tens of billions of potentially habitable planets that may exist throughout our galaxy, each estimate carries within it both the precision of careful observation and the humility of acknowledged limitation. We observe only the nearest fraction of our cosmic neighborhood, detect only the most easily visible planetary systems, and can analyze atmospheric conditions only for the most favorable targets. Whether Earth represents a precious rarity, one among perhaps millions of life-bearing worlds, or stands as a more common example of what cosmic evolution can achieve under suitable conditions, the search itself has already transformed how we understand our place in the magnificent expanse of space and time. Each photon of starlight that reveals information about a distant world connects us across impossible distances to environments we may never visit, but can now begin to comprehend. The gentle rhythm of discovery continues each night as telescopes around the world and in space accumulate patient observations, gradually building our understanding of the cosmic environment that gave rise to our own remarkable planet. Sleep peacefully, knowing that while these profound questions may take generations to fully answer, each new measurement brings us closer to understanding whether we are alone among the stars, or part of a universe rich with worlds, where the chemistry of life unfolds under countless alien suns.